Alrighty, so welcome back, everyone. Where we left off the other day was talking about neural networks, output thresholds, all that. All right, but I want to circle back to that for a second because that's going to drive the rest of what we talk about. So, the neural network model we created and discussed Tuesday was a deterministic model. Okay? Deterministic is a fancy word meaning no randomness. All right? Large language models like ChatGPT, though, they have some randomness built in. This creates some interesting problems. Okay, so ChatGPT and the like contain randomness, right? This is why same request can easily get different results. And more so depending on the complexity of the request, right? So if you ask it like 100 times, what's 2 plus 2? Chances are you're probably going to get 4 every time, although there might be a few weird outliers there from, literary quotes that they say 2 plus 2 is 5, stuff like that. They might happen, right? But in general, a simple request probably going to get the same results more often than not. More complicated requests, like here's an AI grading prompt and here's a set of questions and the student's answers, put them in the system, tell me what you think. Yeah, there's going to be some wobble in that. So, how does that work? Well, let's go back to our old question. All right, we had a line about a cactus. The cactus was tall and, okay? So let's think about how this neural network model gets implemented. We have here the cactus was tall and, right? Finish that sentence. Well, remember we talked about how the neural network is structured, that there are many, 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 many thousands of neurons in each layer, right? And they're all being combined and interacting in different ways as you go down into the model. So I'm not going to draw all these hidden layers. I'm not going to draw all these hidden layers, but you get the idea. Damn it, Beavis. You get the idea. There's a lot going on here. Okay, and then I'm going to draw that once more. Move it up. All right, great. All right, so, these are all combined in various ways throughout the neural network, and we don't have to draw every possible combination, but just so you get an idea that something like this is what's going on. Okay? So, how is this going to work for cactus, for example? Well, each one of these little word combinations is going to be a unique characteristic, right? So it could be, for example, first word, the, and it could be second word, cactus, and third word, was, and fourth word, tall, and fifth word, I guess that's what we have to work with, is and, right? And then it's going to look through and say, okay, that's fine. What about first the and second cactus? Is there something unique about that combination, right? And maybe in the third tier, it goes and combines those first 3 words. Is there something unique about this combination? Okay. And so on. And each one of those, it's going to come up with a result. Now, we talked about the standard model was that each neuron outputs a value, receives inputs in a 0 to 1 range, right? Maybe with square brackets because inclusive, and produces output in that same 0 to 1 range, right? But how do you convert words to that kind of result? How do you convert words to a number between 1 and 0? It's weird, right? How's that going to happen? Well, one thing they use is basically frequency models. So I guess I'm gonna pop out a new window here. Sure, no, let's not save. Okay, boom. Okay. I suppose I would be surprised if anyone here has heard of a zip distribution. Anybody ever heard of a zip distribution, ZIPF? No. Like I said, I would have been surprised. It'd be cool if somebody had them. Okay. The zip distribution is a commonly occurring natural frequency distribution for rankable events. Okay. So one kind of rankable event is the frequency of common words, right? The commonness of words in ordinary speech. So what's an example of a word so common in English, it would be unusual to see a sentence or an entire paragraph without it? What do you think? What's a very common word in English? The. I'll take the. What else you said? Somebody? A. Oh, yeah, a or an. So yeah, words like the, a or an, I, you, he, she, we, they, right? Those are all very common words. Agreed? Yeah. Okay. Maybe collectively that set of words makes up about 20% of the words in, usual conversation. At any rate, you could find a chunk of words that did make up 20%, right? And on the other hand, there are some very unusual words. I'll throw out some unusual words. Zizava, which is alternately a plant or an insect that lives on the zizavad plant, right? Eats on it. What else? Some other very unusual words, unlikely to be seen in real life. Zizava is such a good one. Yeah, I don't know. Very unusual words. Anybody want to toss out a couple? Facsimile. I'll toss that in near the low end for sure. But it's not so unusual that like most of you have never heard it, right? But yeah, that's definitely pretty unusual. Uh, let's see. I could dig out some from my daughter's spelling bee. There's some very, very oddball ones there. Well, you get the idea, though. I don't need to really dig out words. Other more common words, school, work, math, news. Uh, the generic for bird is probably more common than the generic for robin. Anybody ever heard of an eclectus parrot? No, they're birds with bright feathers, right? That's a pretty unusual one. I think most of you could have gone your whole lives without ever hearing the word eclectus. All right. Anyway, so there's this distribution of words. And this distribution, even though it's all words, it can be scaled to frequencies, right? So that's basically what this large language model is doing. Oh, I lost it. When you have that neural network, essentially the output of each neuron, it looks at the approximate frequency of the words involved, somehow scales that to numbers, and then the output, it says, well, based on those, let's create a zip distribution or something like it of all the possible outcomes of that combination of words. All right. And then it essentially picks a random number from that range. That's why you get the randomness. Okay. So anyway, that's the gist of it. So the difference is this first model we did with neurons where we had cases where they were male and female, and men tended to be taller and heavier and women not, right? That's pretty deterministic, right? We recognize that the results aren't going to be perfect. There's going to be some classification errors, but with large language models, the classification errors aren't really the point. The point is you have to, produce a reasonable sounding word. And there could be many possible reasonable sounding words, right? It's not just a right or wrong conclusion. All right, so a little bit different. So that's our preamble. And so that brings us to the actual lecture. All right, so the same general model gets used for large language models, right? There is a neural network. Each neuron accepts a couple of, some combination of words as inputs, right? So the input data is a set of words. Each word or each word group gets somehow converted to a number on that 0 to 1 range. And the way it figures out what are sensible outcomes is based on the training data. So all of the text data that got gathered from every corner of the internet, the large language model looks at that and says, what is a plausible conclusion to the cactus was tall and, right, based on that. So if you have bigger models, and by bigger, we include both, number one, a larger, and richer, more diverse set of training data, right? You're going to get more realistic, more correct outcomes. But you also have the problem that if you try to extend a model to a new case, it could give you the wrong answers, right? So, for example, suppose your entire discussion of cactuses in your training data just said, yep, cactuses are tall and green, right? You don't see much else. Then it's pretty likely that that's what that sentence is going to get filled up with, right? Tall and green. But if you include examples from literature that are, more metaphorical, right? The cactus was tall and angry. The cactus was tall and threatening. You have the possibility of getting those words, even in contexts where it seems a little off to do that, right? So the fact that you're getting a richer set of data does also inherently create the possibility of having weirder outcomes. Okay. So, but in general, yeah, bigger model. If you have more neurons, they can handle more variables. If you have more hidden layers, then they can look at more complex interactions and be more likely to give a sensible answer. And of course, more training data overall is going to give more reliable results. But, it's not simply a matter of saying, gosh, the more training data we throw in, the more perfect our model is going to be, right? At some point, by introducing new training data, you're also introducing the possibility for more weirdness. Okay. So you kind of have to do all three. So talking back to this was a thing that became big in the aughts. So way, way, way back when, Google just did search based on exact text matches, right? So talk about this. We got time today. All right. Say way back when, so circa 1998, when most people first became aware of Google. Circa 1998, Google did search results on the basis of exact text matches, right? Basically, if the page did not contain the exact search text as entered, that page would not show up in the search results. Okay? Needless to say, this created a fair amount of frustration for users. Because why? Why is this frustrating? Why is this not giving users the results they hope for? Yeah. Right. So what do they have to do? Figure out exactly, right? So the root thing is because the same idea, right, can be expressed in multiple ways, right? So an obvious one for this, World War II, right? Often expressed as World War II or the Second World War, right? Or WW2 or WW2, right? Back in the day, if you were looking up some information on that, you would have to hope that the search pages you look for had that information in exactly those words, or it wasn't going to show up. Okay. And this, obviously there's a lot of other things that happen that way. For example, if you tried to do how is New York City commonly abbreviated? NYC. Okay. Back in the day, you couldn't look up NYC and get the same results or vice versa. But now you can. Well, how does that happen? How does that come to pass? All right. Did Google write some super smart AI brain that could figure this stuff out that said, aha, this means the same as this because I understand language? No, of course not. Right. All that, this was a change, starting in the aughts, right? The zero zeros. And, basically being implemented starting around 2010, Google was able to recognize term equivalence. This was a really big step forward, right? It meant that you could type in something and Google could figure out, this thing is the same as that thing, right? Well, the way that they did it was simply tracking user behavior, right? So, how might Google figure out that two terms mean the same thing, right? Bearing in mind, they only have a few things. They have the pages themselves, but not AI to interpret page content, right? So they just have the pages and they have the searches done by users and they have the user reactions to those searches, to those search results, to any presented search results. All right. So how does Google figure out the two terms mean the same thing with just that little bit of information? Under what circumstances would Google figure out, these two searches mean basically the same thing? Yeah, maybe, but how's that going to let Google figure out? I mean, that could be a factor. I'll give you that, right? So could be a similarity factor regarding frequency, right? But that's not regarding search frequency, but that's not going to really give you the whole answer, right? It's just going to say these things might be the same, right? Likewise, probably would not reliably include uh, the similarity of the terms themselves, right? Because there are a lot of words that sound the same but are very different in meaning. So, what are you going to do if you type in two different sets of search terms that mean the same thing? How are you going to react to the search results? Give an example. Suppose you're in Chicago. You are in Chicago in April, okay? And you search for Cubs in one search and search for Chicago Cubs in another, okay? The Cubs search might give you, you know, might give you MLB stuff, Major League Baseball, Chicago Cubs team. It might give you something about Bear Cubs. It might give you something about baby, what other things are cubs? Wolves or pups? Or bears or cubs? Baby bear cub born at Lincoln Park Zoo. Okay. Dot, dot, dot. Teddy bear cub stuffies, right? Whatever. Uh, and some dude dressing like a furry to do bear cub stuff, arrested in downtown Chicago. Okay. That might be the set of searches you get. But you're searching for cubs, right? So which one are you going to click on? Duh, of course, right? We're going to click on MLB stuff, right? Yeah, okay. So in the other one, we do Chicago Cubs and we get a different batch of results, right? Obviously. So we might get what might carry forward. Well, the MLB stuff, the MLB stuff is probably going to carry over. We'll probably get multiple things about Chicago Cubs there, right? We'll get Chicago Cubs Wikipedia article. Okay. Maybe we will, in fact, get something about this baby bear cub born at the zoo, because in case people didn't know, Lincoln Park Zoo is in Chicago, right? And this guy got arrested. He'll probably be in there. And maybe some more baseball stuff. So we're still searching for Chicago Cubs, right? What are we going to click on? Well, there's a good chance we click on this. Maybe we click on this, right? And those are at the top. Those are probably the ones we're going to click on. So Google is going to recognize, hey, there's a lot of overlap between these searches, right? Maybe Cubs and Chicago Cubs, at least in a Chicago near data center, maybe those mean the same thing, right? So what it's going to look at, what Google's going to look at is basically if two searches lead to similar search results, similar user clicks, similar user not going back and revising search, Google can reasonably infer that the terms mean the same thing, right? And increasingly so with the similarity of results and behavior. Okay. That's how Google figures it out. They compared these things and they said, gosh, you know what? Let's look at if there are sets of search results that have no overlap, Google can pretty much ignore them, right? But if they start seeing the same page appears on a bunch of different searches and gets clicked on a bunch of different searches and gets stayed on a bunch, then Google could say, hey, this is a good candidate for looking whether these things are the same. And it starts learning based on that, right? And once it does figure out the terms are the same, then it kind of indexes that as a permanent result. It may, periodically revise that assessment. But in the short term, yeah, Google's going to recognize, at least at this point in time and space, Cubs is a reasonable substitute for Chicago Cubs. All right. So that was what all this was, right? And so again, same thing is going on for large language models when it tries to find similar terms, But this is something that has to get worked out in number one, assessing the training data in the first place. Basically, if you look at all the different factors involved in predicting the next word, and you find that one factor is not doesn't really distinguish between outcomes, then you could say, okay, yeah, those things are functionally the same, right? So you might, for example, say something like, the cactus was tall and blank, leads to a pretty similar set of outcomes as the cactus being short and blank, right? Those are probably about equally likely to end in the word green. But are tall and short the same? Of course not, right? But for purposes of the content that the large language model is going to produce, in this particular context, yeah, they're about the same, right? Okay, so it is a strange puzzle. This is the kind of puzzle that LLMs have to work with a while, and this is why they do in fact need a lot of different inputs from different sources to try to fix problems like that. Okay. So now you've probably heard, I mean, I know you've heard it from me. You probably have been aware of it before that platforms like ChatGPT and other AI things, they go out and they scour the internet for content, right? This is a known thing. You didn't need me to tell you this. Yeah, okay. So again, one of the big sources of this is an operation called Common Crawl, right? So we can, you don't see it, but I see it. Okay. Common Crawl maintains a free open repository of web crawl data that can be used by anyone. It's been around since 2007. It's been helping out a lot with this stuff, right? So we could ask, I even go to ChatGPT and ask them, hello, good sir. How much of your training data comes from the Common Crawl open repository? No, I'd heard about 30%. I thought it was gonna maybe be a little bit more forthcoming, but let's see. I had heard it was in the ballpark of 30%. Hmm. Searching for on the Atlantic. It's a wire. Okay. Aha. Okay. All right. So raw crawl text. Yeah. Okay. Okay. Hmm. Interesting. Okay. Well then. But here, this is good, right? 60% by training mix weight. So that is a big chunk of, the impact of the data. So, right. Cool. All right, am I not? What's going on here? That was weird. Okay. So we covered that, covered that. Anyway, all of that text data trains the large language model. So essentially training in that sense, remember every neuron has a little mathematical function in there, right? Takes a couple inputs, does some math on them, reduces the output to some 0 to 1 range, right? That's the math that happens. Well, you calibrate those different mathematical functions, you'll get different outcomes. If you say this neuron is more important than that neuron, if you say the first two words in a sentence are a lot more important than the middle two words or the last two words, you're going to get different outcomes in the text that gets produced. All right. So what they do is over and over and over, they test out different functions, different thresholds for what processes happen, how significant it has to be to keep it in the computations. And eventually they arrive at some batch of output that they figure is about good enough, right? It's not going to be perfect because again, it's like bubble wrap, not bubble wrap. It's like that stuff where you have a bubble on your screen protector on your device and you kind of smooth out that bubble and it pops up in other places. It's kind of like that. All right. So the expectation, just like Google is not going to deliver perfect search results, and it's never been expected to give you perfect search results. It's designed to give you pretty good search results, right? Same kind of thing. The expectation for large language models is it's not going to be text that's actually, thoughtfully produced. It's basically going to be a reasonably coherent simulation of thoughtful text. That's why you get some weird stuff. All right. For example, all of this text data included in the system is time bounded, right? So unless they do updates, right, whatever's in that initial training data, that's what the LLM is going to think reality is. So sometimes you can get outdated stuff, right? So there would have, if all of the data was compiled pre 2020, it wouldn't have information on all the other stuff after 2020. So you might ask it a question with, what's going on with Russia's war with Ukraine? And you're like, war, and it'd be like war with Ukraine. Are you talking about the collectivization famine in the 1930s? And you'd be like, no, I'm talking about 2022, right? But it wouldn't have had that information. All right. So anyway, all of that sort of thing, right? It's also time bound. So, okay. Now, all of these interactive applications, they need to give humans sensible responses, right? So, basic question, how does the AI recognize questions and match them with answers? So, again, this is a qualitatively different problem from just saying the cactus is tall and trying to figure out the next word, right? It's basically flipping that around and asking, if you ask it a question, it has to look in all of its data and try to figure out what's the proper way to answer this question, right? Like if the initial text is in fact this prompt that the user enters, what makes the most sense to follow that prompt? Yeah. And this, again, this has a lot of trouble. So there's an interesting article on that. Some dude gathered up, untold piles of Reddit data and tried to figure out when AI, improperly evaluated human responses. So the idea with one of those, I mean, first of all, some questions around perplexing are simply questions that are more open-ended, right? AI tends to do really well with simple facts, like, when did Christopher Columbus come to the New World? It's going to tell you 1492, right? But if you ask it some question about, what would be the probable consequences of Spain attacking Gibraltar in 1940, then, that's going to be a lot more open-ended. It'll probably look at a lot of hypotheticals out there and it'll say, well, we really don't know, but well, here's what people have thought on the internet, right? So sometimes, in general, questions with clear, simple, unambiguous answers tends to do better with. Also, of course, questions that a lot of people have thought about. There'll be more examples of that in the training data, right? In particular, questions that a lot of people have thought about it the same way, right? In the same context, in the same way, is going to give better results. But sometimes when it's doing just simple conversations, it's pretty easy to throw it off the rails. So a typical conversation on Reddit, right, might go something like this, right? User one, I think UIC isn't quite as bad as people say. And user two says, why would you say that? Have you even seen the CS department? And user one would respond back, okay, CS people can be gross, but I'm a business major, so I only see them walking around, I guess. User two, yeah, fair. Okay. User three chimes in, really though, we should all be thinking more about walruses, right? When you throw in something completely random like that, and this thing on Reddit, it might get like 50 thumbs up in that context, right? Just because it's random and stupid. And that's going to be very perplexing to the AI because they're going to think that, oh, it got 50 thumbs up. That must be a very thoughtful and, resonant response to this conversation. And that's going to fuck up its own responses for decades afterward. Okay. So this is that sort of thing too, is that humans are not always sensible. The AI is trying to be sensible, but yeah. Okay. So the solution to all that, again, as far as humanly possible, try to find comparable questions and answers in the initial training data, right? Not always going to be possible though. Another thing they do is they link these systems to external repositories, right? Things that give terms, give definitions, give pre-existing responses. the zip distribution applies not only to word frequency, but to topic frequency as well, right? Like you could look up, the top topics of any particular day, and some things are going to be a lot more commonly discussed than others. And so the large language models are naturally going to prefer to focus on those because then they get, the most users happy with their responses. Okay. And of course, all this built in is the assumption that those answers are correct. All right. So there's any number of false assumptions out there. Let's see. Let's see what ChatGPT says. Oh, yeah, here. Can you give an example of a widely held false assumption that has afflicted your own training data? Hmm. Holy shit, here it happens. Oh, all right. Well, there you go. There's something, right? So the thing is, if a lot of people talk about left brain and right brain as if it's a lot more important than it actually is, that's going to affect the output that ChatGPT delivers. Okay. And weirdly, ChatGPT is able to recognize this. All right. All right. Okay. So the first question, right? How useful is the neural network right out of the box, right? You go to ChatGPT, you throw a question at it. Sometimes it gives you good answers, sometimes not, right? On the whole, it's a pretty good tool for topics that are frequently discussed and don't require a whole lot of really detailed domain knowledge. All right. So if you ask it a simple fact-based question like how many pecks are in a gallon, it'll give you the right answer to that, right? Other things, specialized questions, or importantly, small deviations from very common questions, maybe not so much, right? So this is a link I'm going to blow up. All right. Easy problems that LLMs get wrong, right? I'll let you, if you want to, you can dig through this, but I want to show you, I think this is the one about Alice's brother. Oh, that's classic. You guys know the old riddle about there's a farmer and a wolf and a goat and a piece of cabbage and a cabbage and he's trying to cross the river, but he has to leave the things on opposite sides. No, I mean I'll write it up for you if you. All right. So this is the basic. A farmer has a wolf, a goat, a cabbage, and a boat. He needs to cross a river using the boat, but he cannot leave the wolf with the goat or the goat with the cabbage, and the boat can only carry the farmer plus one, right? That must be a very large cabbage, but he can only carry the farmer plus one. How can the farmer arrange ferries back and forth to cross the river, right? So the answer to this one is something like farmer takes, uh, who goes across first? Farmer takes the wolf. No, if he takes the wolf across, he leaves the cabbage with the goat. That's a problem. If he takes the cabbage, he leaves the wolf with the goat, right? So he's got to take the cabbage. Cabbage takes cabbage first. No, then he leaves the thing with the goat. Who does he take? The wolf, the goat? Oh, he takes the goat first. Okay. Drops it off on the other side of the river. Comes back, takes the cabbage. Okay. Drops off the cabbage across the river, then brings back the goat. So the goat's not left alone with the cabbage, right? Then brings the wolf across the river, right? Leaves goat there, drops off wolf, safe with cabbage. Then goes back and gets the goat, right? Problem solved. Gets the goat, brings the goat back, boom, they're all over on the other side. Anyway, so that's the riddle, that's the solution. And then one of these things, because it doesn't actually solve the riddle, it just looks at predictive text, you see wacky shit like this. Now the farmer can safely leave the wolf with the goat because the cabbage is no longer a threat. All right. There was a simple, another one, right? It's probably in here somewhere. Alice. No, maybe not. It's somewhere in one of these links that I have, right? Alice has two brothers. How many sisters does Alice's oldest brother have? How many sisters does Alice's oldest brother have? One, yeah, right, just Alice. Right? But sometimes the thing gets it wrong because there could be any number of similar statements like that, right? But it's not actually solving the problem. It's just trying to do some predictive text from a random distribution, right? So, anyway, one of these articles, like I said, talks like that. So, the future on these sort of things is basically to build logic modules, right? So, one bubble is going to have the text, right? The prompt text, and it'll get sent to some sort of logical analysis function, right? Logic uh, analysis test. Is this a logic problem? If it is, then it'll get sent back and forth, then solve it. Otherwise, ignore it, right? So if you ask it a question that's a simple fact lookup, it'll say, okay, blah, 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 here's the answer. But if the prompt text looks like, this might be like asking some sort of problem that requires a solution, it's going to need to get sent up to a higher order of analysis. Okay. But again, providing that sort of free form logical problem recognition and analysis and solution, that's going to be a lot more expensive than just throwing random answers from a large language model. Okay, so the zero shot model, the zero shot prompting means you ask the question, hopefully the model gives the right answer, right? Few shot, on the other hand, means you give the large language model a few examples of what you'd like considered. Basically, you direct the search and say, I know you have all of this training data you've worked through, but consider this to also be part of your training data. I'm going to give you a few good examples. Okay, so for some things, zero shot's going to work great. For others, you'll have to do a few shot. For example, when I'm grading exams, the first few that I run through on this, it gives kind of weird results, often like too generous. So what I do is I give a bunch of results one day, and then I come back the next day. It's basically I've given the system some time to think about it. I come back later, and I tend to get better results. Right. And when I mean better, I mean more in line with my plan of, A, being slightly generous with the grading, but B, not falling for obvious circular bullshit. Right. So, yeah, I was just grading some things today, and there was a little bit of that, for some questions, AI wasn't quite getting it, wasn't quite getting that people were evading the answer. All right. So, anyway, in particular, general large language model, if the questions that you ask are aligned with its text distribution, it's going to do pretty well, right? So, for example, if you ask it the ordinary question, how are you feeling today, right? In probably the vast majority of its training data, how are you feeling today is associated with someone's emotional state, right? Are they happy? Are they sad? Are they bored? Whatever, right? But maybe this is an application that's being used for medical purposes, right? And the doctor is not really, the doctor certainly wishes you well, but the doctor is not overly concerned with any of those things. More looking for specific symptoms, right? My ankle is swollen and sore. I can hardly walk on it, stuff like that. So, different kinds of tuning, right? So, what they do in general, it's like the few shot approach. I was trying to do that. It's like the few shot approach, but you can also upload supplementary batches of text, right, to upload the model calibration. So the way this works in general, right, is a typical business, right? So let's draw pictures. ChatGPT builds the model, builds general model. See if I can fit that all in a little better. There we go. ChatGPT builds the general model, and that is going to be oh, that was weird. All right. That's going to be something that can be widely used by a bunch of different users, right? So different businesses might say, hey, I'm running a CRM application, customer relationship management, right? Here's my product information and common customer concerns, right? And then that'll be integrated into ChatGPT's general model to be more useful, right? Or, for example, I'm running a chatbot for, I don't know, airline reservations, right? Here are the typical customer concerns for this domain, right? And it would be like typical examples of customer conversations, typical searches in their database, what they're looking for, typical terms and definitions, right? So the, flight in the context of airline is a little bit different from the generic use of flight, right? Flight generally means a specific trip. So stuff like that to get better fits, right? So ChatGPT has the general model that essentially understands English, can produce coherent output, but it still needs to be somewhat guided to perform well in a specific domain. All right. Anyway, now suppose we're talking about accuracy, right? If I offer you two versions of a model, how do you as a user determine this version is better than that version? All right, that's the basic accuracy problem. So, first thing, how do you measure accuracy in general terms? And second, how do you cross compare different kinds of inaccuracy? Okay, so for any sort of classification problem, right? We had our old example where we had a person, we got their height and weight. We say, is this person male or female, right? That's a classification problem. And maybe the answer from our model is right, maybe it's wrong, but the further the person is from that split curve we drew in the middle of the data distribution, the further they are on one side or the other, the more confident we can be in our classifications. All right. But the first starting point is simply accuracy. So accuracy is how many events are predicted correctly. All right. So if you toss out a batch of 1,000 people and the system correctly classifies 810 of them as properly as male or female, we'd say that system has 81% accuracy. Okay. So accuracy doesn't at all distinguish between different classification errors, and it's not very useful when the overwhelming majority of data is one kind of thing, right? So imagine for network security, right? In network security, the vast majority of actions, of events, are going to be non-threatening, right? They're going to be legitimate activity. There's going to be a small fraction of events that are associated with security threats, right? So if you have a system that gives you 99% accuracy, it could get that easily by just classifying everything as not threatening, but that wouldn't be very useful. So those kind of models. So accuracy for some problems, it's good enough, but for other kinds of problems, it's nowhere near good enough. All right. So the next thing is to distinguish between different kinds of problems. All right. So positives and negatives. So the way to think about this, you ever watch one of those police shows and the cops are chasing somebody and they see it's the bad guy and so they yell back to the station, "Oh, we got a positive ID on our target," right? Positive ID. That means this guy is the guy. A false positive logically would be then the person is identified positively, but is in fact not the bad guy, right? It's a false positive ID, false positive identification. So, classification events could predict a person is either a man or a woman. Both of those could be wrong. So, an example of a false positive would be the model says the person is a man. It's not actually a man, it's a woman, right? False negative would be the model says the person is not a man, but it turns out actually is a man, right? You made a negative identification. You said the person was not this thing, but it turned out they were. Now, in this case, our data only has two types, right? We only talk about men and women in this model. So they're going to be symmetrical, right? If you say man, is not a man, that's false positive. It's going to be equivalent to saying not a man, but turned out it actually was. All right. Anyway, because there's only two options. Anyway, so there's some advanced accuracy measures in this case. Number one, there's recall. So recall is the number of actual positives that are correctly identified, right? So if your database has 500 men in the sample and you correctly identify 495 of them, that's 99% recall, right? You're successfully identifying 99% of the men. If you, right, say percent of positive events that are correct, that would mean suppose you made 500, what should we do? 500 and, should we do the same thing? I'm trying to work out the numbers in my head. I'm a little bit blanking out. Well, precision is however many events there are, right? How many of those are correct, right? So of all the times you identified a person as being a man, what percentage of those were in fact correct identifications? So this is the difference. So recall, you could say, well, I'm going to go through this database and I'm going to identify 995 of the 1,000 individuals as men, and it turns out that there's 500 and you got 495 of them. Yes, you got very high recall, but you didn't get very high precision because you only had about half of the positive events being correct. You identified an awful lot of women as men. Okay? So that's the distinction between recall and precision. And of course, false alarm rate, right? Actual negatives wrongly identified as positive. False alarm, the good way to think about that, what's a kind of event that would be really alarming? Suppose you go to the doctor and the doctor tells you you have, that would be alarming, wouldn't it? I think it's fair to say most of us would be alarmed if the doctor told us that. But what if it turned out the doctor told you this, and then a week later they said, "Oh, sorry, man, we read your blood results wrong. You're actually fine, no cancer." You'd be like, "Ooh, false alarm," right? That's what we're talking about there, right? So it's an actual negative. The event should be you do not have this thing, but it was wrongly identified as positive. Now, again, depending on the situation, recall, precision, false alarms, they may be more or less significant, right? So just some points for thought, right? What do you think is more concerning? If an email is wrongly identified as spam or spam is wrongly identified as not spam? In the first one, what happens if a legit email is identified as spam? The person doesn't get it, right? It goes into the spam folder. They probably don't see it till weeks, months, years later. Okay? What about spam being wrongly identified as not spam? Well, definitely it's going to clutter up your email box. Also, a lot of spam contains bad stuff, doesn't it? So, right? It's kind of hard to say. They're both not good. I guess if you had to err on one side or the other, you'd probably be making sure that all of the legit email got to the user, right? Probably, but you can kind of see their point if they're like, oh man, we got to be careful about this too. Okay. What about if a purchase is wrongly identified as fraud, or fraud being wrongly identified as not fraud? The real problem there, what happens if a purchase gets wrongly identified as fraud?
Legal consequences,
What's that?
legal consequences for the person accused.
Probably not immediately. Anybody ever gotten a fraud alert on their credit card when they tried to buy something legit? Like you've been up drinking at 2 in the morning and you decide to buy some expensive front row concert tickets, and the bank says, "Hey, wait a minute, you don't spend $2,000 on concert tickets, right?" Yeah. So probably not illegal off the bat, right? They block the transaction, right? And so what happens if the purchase is wrongly identified as fraud? Chances are it's just a hassle for you, right? You got to call up the credit card company and be like, no, no, it really is me, did this. Okay. But what about fraud wrongly identified as not fraud? Who pays in that event? If somebody gets away with a fraudulent purchase, does that cost you anything? If somebody steals your credit card and it doesn't get identified as fraud? There's a good chance it costs you, but you can complain back to the credit card company and say, hey, I didn't spend $2,000 on those tickets, right? And they'll say, oh, so sorry. Let's delete that charge. I don't know why our fraud team didn't detect that. And that is what'll happen, right? There was a thing, for some reason, somebody had gotten my credit card number and used it for a long-running Microsoft Azure subscription, right? And I caught that, and the charges went back several months, and I got all the money back for that. So that was nice. Okay. But anyway, in this first one, the hassle goes to the user, right? The card owner. In this case, chances are the charge goes to the credit card company. Although, yeah, you might be on the hook for it if you're not checking your statements. All right. Similar things. What happens if a medical test wrongly identifies cancer? That's going to be a problem, right? Because that's going to probably lead to a lot of unnecessary and expensive medical procedures. Okay. But what about cancer wrongly identified as benign? Benign meaning harmless. This is bad, but this is really bad, right? But it depends, because some cancers are more dangerous than others. If you're old, for example, if you're in your 90s, my wife's grandfather got diagnosed with cancer about, a year before the end. And they said, yeah, you have cancer, but something else is going to finish you off before this does. It's one of those real slow ones. My brother developed a rare slow form of leukemia late in life, around when he was 40. And he died of something completely unrelated several years later. But they said, yeah, we'll keep an eye on this. It is cancer. It's not good, but this probably isn't going to be what finishes you off. So again, situationally, it kind of depends. On the other hand, my wife's grandmother got pancreatic cancer. And if you know anything about that, that just tears through you fast, right? She lasted about a year, which was way longer than they expected. So last ones, network security threats wrongly identified as safe, or safe events wrongly identified as a threat, right? Again, this is like the credit card example, but exponentially maybe more dangerous, right? If a network security threat gets wrongly identified as safe, that's like basically leaving the gate unlocked for a while. That's probably a very big problem. Safe events wrongly identified as threats, that's probably annoying, but not, critical. But it does depend on the relative frequency and severity of those problems. All right. So anyway, just little discussion about different kinds of pros and cons of different kinds of inaccuracy. All right. I mean, of course, everybody would like to be their model to be accurate all the time. But what generally happens is if you push down the false positive rate, you bump up something else, whether it's false negatives, false alarms, whatever. All right. So Again, even a model with very high accuracy and very high precision and recall is not necessarily good. This is called overfitting. Where are we time-wise? Oh, 4:30. Okay. So I'm going to do a quick discussion about this. We'll go back to hot dogs. Remember we talked about hot dogs? Yeah, you don't forget something like that. All right. So imagine if all of your hot dog data, your sales data, followed a trajectory. Oh, shit. Followed a trajectory like this. And we can see, our axes once again, we'll mark them hot dog sales and attendance, ball game attendance. Okay. Now, the sensible thing to do in this case would be to simply recognize that there's going to be a bunch of little factors you can't fully account for in your model, plot some reasonably tight line that fits all of that data, and assume it's pretty close but not exact, right? That is the sensible thing to do. The not so sensible thing to do would be to draw a bizarrely convoluted, we'll draw it in orange, a bizarrely convoluted model that does something like this. And hits every data point perfectly. Okay, you get the idea of where I'm going with this. I'm not going to push it into the ground, but you get that, right? Now, it is true that if you come up with some screwy curve like that, it will fully capture every data point in your model. And if all the data in your future scenarios do in fact have the exact same context and the exact same factors and the exact same ballpark attendance, yeah, it would give you those proper results, right? If you run your old training data through that model again, it would give you those exact results, right? But what if the data points going forward, in fact, are distributed similarly, but, so distributed around that line, but not around that curve, okay? This curvy model is going to be pretty useless, right? It's going to be way worse than the simple, cheap regression line that, any first year statistics student could put together. So this orange curvy line is what's overfitting. You're basically designing the model specifically to fit your entire set of data. And because of that, it's going to be a really, really weak predictor of future results. Okay, so, and ways that can happen, right? Too many variables, not enough training data. And again, the extreme case, writing a set of separate functions that exactly predict every training point, right? If you say, if the attendance is X, the outcome is Y. If the attendance is X2, the outcome is Y2, right? If you just have a simple list of those functions, that's not going to work very well. So common ways they do, number one, get randomized data training subsets, right? So you train your model on a random half of your data, and then you test it for accuracy on the second half. That's how you can avoid that kind of overfitting. If you want to do it a little better than that, you could, for example, train it on like 3/4 of your data and maybe test it on 1/4, something like that. Uh, and also monitoring response quality on new data. As new events happen, is your model giving pretty good results compared to, for example, a simple regression line? Okay. Now, what to do when your model produces garbage, right? So you guys have surely heard of AI hallucinations, right? It makes up shit. And that's because the nature of the model is it has to invent something for every step. Every time it produces a word, it looks through the results of that training data, it generates some text. If it doesn't have real stuff, it'll just generate something that kind of fits in with its results. Plus, there's always randomization in there, right? If you ask it to look up a particular literary reference, yeah, it'll probably find that exact thing. But if you ask it to, create a set of references for an English paper, it's just going to throw together some, fairly random stuff. There'll be popular authors, popular books, popular page numbers, right? But they'll all be kind of jumbled together because of the mix of data and the randomization. So, uh, anyway, if there's low frequency of relevant words and phrases in the training data or different contexts, you're going to get garbage, right? If your information is outdated or just bad, right? If the internet believes something, chances are your large language model probably also will. For a long time, when I was looking up stats on the global population of kiwi birds, for example, it would give me outdated stuff because there are a bunch of charities out there in New Zealand that are doing efforts to, basically hunt predators of kiwis and keep them safe. So they always are a little bit alarmist, though, right? Like, kind of like any activist group, they're never going to tell you, hey, the world is great. We're fixing the problem. No, they're always going to say, we're in crisis. Please send us your money, right? So they always use like slightly older numbers. So they give the number, even on like current sites, you could see numbers when like the kiwi population was at its bottom, like in the 90s or the early 2000s. Uh, anyway, and sometimes overly complex prompts, right? Although that depends on the platform you're using. I've heard with the new Claude system that they use to generate actual production code that you sometimes need to put in prompts that go on for multiple pages to really get the results you want. But I guess still, if you throw in overly complex stuff past that, at a certain point, it might be counterproductive. So, general approaches to solving this. Number one, make requests in smaller, simpler chunks, right? Especially if you're using basic chat GPT, not the professional grade stuff. Cross-check results, right? If there's a response in there that seems kind of weird, you know what? Maybe just Google it, look for yourself. And ideally, have enough technical knowledge to say, if the AI gives you something weird, that you know it's not true, right? So you guys were here the other day when I was having a little problem trying to get the number of cores in a GPU, right? And I use some different terms, right? I was like, how many chips does it have? And I say, chips, no, there's just one. I was like, that's not the kind of chip I mean, right? And I finally said, oh yeah, I used the word cores, and cores worked and gave me the answer, right? But if I hadn't known that, I could have walked out of here saying, yep, there's just, there's one thing in there and that's all there is. But there isn't. All right. So, other stuff, image classification, right? Just a couple more slides. So, another AI that is improving rapidly is image classification, right? Now, this is a problem that AI has struggled with for a long time. And humans, in a lot of cases, they get it kind of reflexively, right? So I'm going to draw a happy face. Okay? And we can all agree, I hope, that what I'm about to draw is indeed a happy face. Fine. It's got the swoosh. Okay. We agree this is a happy face? Right. So the AI, basic AI, would look at this and say, aha, two dots, kind of round, got a curvy mouth thing. Okay, there's no nose, there's no ears, there's no hair, there's no necks. Maybe it's a stylized happy face, right? It fits in pretty well with its library of training data for, stylized yellow and black happy faces. And it says, okay, this is a happy face. But if you do something very simple, like you do this and this and this, I guess I'll capture the whole thing. And we have the happy face hiding behind a few sticks of bamboo, right? This is suddenly a far more difficult problem for the AI. We can look at this and we're like, oh, yeah, that's a happy face stuck behind some bamboo there for sure, right? But the AI looks at this and says, this curve, that's not a circle. That's like, I don't know, maybe something like a half circle. Here's a weird angle. What is that? What kind of shape? I don't know. It's kind of a trapezoid. And it's going to have a lot more trouble recognizing that as a face, right? The more advanced ones, yeah, they can do it, but not as easily and consistently as humans do. All right. So, what happens with image classification is generally the AI uses something called feature analysis, right? Little portions of an image that are reduced to mathematical functions like lines and curves and sometimes with colors mixed in, right? Just like it does with text, it recognizes which features matter, which features don't matter, and looks at them in little pieces, right? And again, if there's enough training data and that training data is varied enough, the AIs can, in fact, even recognize those deviations, right? But this is image classification, much more difficult, complicated problem. Last thing, LLMs may well be hitting the wall, right? So a lot of things in the real world, they start off pretty well, but eventually they get diminishing marginal returns, right? Where more effort doesn't deliver the same increase in results. So basic neural networks may have already hit the wall, may not have that much room left to improve. Doesn't mean AI is dead. It means that, we're looking, the future is going to be some kind of multi-layered system, right? There's going to be a basic text module. There's going to be logic analysis modules. There's going to be other features built onto that. There'll be different kinds of logic. That's what's going to happen because LLMs by themselves, they're simply not achieving it. I guess I got to hit it here. There we go. Hope it gave me the link. Uh, let's see. I'll have to do it this way. Okay. Here we go. From Substack. This is from 2024. And I'm just going to zip through this very simple thing here, right? So this is the change in a few months. They have a more extensive one, but basically everything is kind of tapered off. And they were getting some big gains in these, right? I don't recall what these particular things, that one's math, but they were getting some big gains in there. But some of these, like yellow and green, are actually going down, right? So the problem is essentially there's limits to what LLMs can do. You can throw more training data at it, but unless the training data matches closely with the questions that the humans are asking, at a certain point, it's just not gonna guarantee success anymore. All right. So there's some other features here that basically say, yeah, some of this stuff is closing out, right? Uh, you get conversations like this: make an image with exactly 17 dots. Here is the image with exactly 17 dots. It's not 17 dots, right? Again, this is not to say that AI isn't useful. There's plenty of things in the world that don't have to work perfectly to be useful. But what it means is AI is not the end, right? Human skills, human creativity still matter. They are working on maybe new models, new technologies that will make us obsolete, but they're not there yet. All right. So you guys still have to get through school. All right. Anyway, that's all I got. Have a good weekend, and we will see you next time.